In high school and early university, math has largely stayed the same. You're given a problem and your goal is to find the solution. But in late university or grad school, you go beyond simply calculating answers. You're expected to reason with proofs. Often at times, you already know what the answer is, and you have to show why it's the way it is. Here is a head-to-head comparison between multivariate calculus, a course taken in second year, and abstract algebra, in upper undergrad or grad subject. Here I'm asked to calculate the flux of a vector field across a certain boundary, and I do so by applying the divergence theorem. As you can see, the answers are very straightforward. It is a simple computational and procedural approach, a common hallmark of earlier math courses. On the other hand, in a proof-based question from higher-level pure math, you write more words than you do numbers. You reason your way through the page with dialectical precision and proper mathematical grammar. No longer is it as easy now as a simple plug and solve. Now, in a different manner, you have to structure your logic and make coherent and sound arguments. Now, let us take you through the content that would be found in a math major. So, a math major, by its name, is very, very vague. There is applied maths, and then there's pure maths. In pure maths, we learn not in order to solve problems in the real world, but that we find out about the ideas behind numbers themselves. In abstract algebra, instead of studying numbers, we study mathematical structures called groups, rings, and fields. These structures help us model symmetry in our universe. This is typically a third-year course in pure mathematics and can be taken as a graduate subject as well. Number theory is all about integers and the tidy patterns they hide, like prime numbers, divisibility, and why certain numbers feel special. It's an old math, but also behind new things like cryptography. This is also a third-year course. In analysis, we study the mathematics that underpin calculus. It's where we get hands-on and intimate with things like limits, continuity, and infinity, to make sure that all parts fit together like a stunning jigsaw puzzle. This class, taken in third or fourth year, is notoriously challenging. So make sure you have the right prerequisites before you try to tackle it. Topology is also called rubber sheet geometry. We don't care as much about shape and angle, and we care more about what doesn't change. Like when you stretch, twist, or bend things, like turning a donut into a coffee cup. Now, this is a subject that's very advanced and infamously challenging, so be sure you know your stuff before you proceed. And it only gets harder when you reach algebraic topology and differential topology, which builds on what you already have with algebraic tools. Now, set theory is an interesting subject, as we learn so much from so little. We don't just learn about sets, we also learn about cardinality and different sizes of infinity, and the bedrock that underpins all mathematics. If you want to look at math from a microscopic angle, you'd stumble on set theory. It deals with logic and foundations. Pure mathematics is deep, creative, and really rather like entering an invisible world. You might not always know where it is going, but it is replete with gigantic ideas which influence all else. Now, applied math is where math meets the real world. Numerical analysis is about getting good approximations when exact answers are too hard. It's like when computers solve big equations. Optimization asks, what is the best way to do something? It's about maximizing efficiency, minimizing costs, or finding the most effective outcome. Mathematical modeling takes real world situations like disease spread, traffic flow, or climate and turns them into math that you can analyze. Differential equations describe how things change, like motion, heat, or population growth, using equations that involve rates and slopes. Chaos theory looks at systems that seem random but actually follow rules. Tiny changes can lead to wild, unpredictable results. You may have heard of the butterfly effect. Now, that's a topic you'd encounter in a course on nonlinear dynamics and chaos. Math is indispensable for polymath, in my opinion. An interdisciplinary student cannot truly be called a polymath if they don't study mathematics. The word math is even in their name for their namesake. Math is the skeleton for the polymath. It unlocks patterns in nature, structure in language, logic in philosophy, and precision in science. Without it, your whole perspective as a polymath will crumble and be meaningless. That's why I made it my goal to self-study both pure and applied math, to appreciate its beauty in itself, and to see where it leads.